Good morning, everyone. Welcome. Today, we embark on an exploration of a fundamental principle in thermodynamics, the zeroth law of thermodynamics. This seemingly simple law has profound implications, particularly in how we define temperature and understand the concept of thermal equilibrium. In fact, it is so fundamental that it serves as the logical foundation for our ability to measure temperature in a consistent and meaningful way. The zeroth law might sound obscure, but it's the reason we can trust that two objects in contact will eventually reach the same temperature. And it provides the basis for calibrating thermometers and ensuring accurate temperature measurement across different systems. It's the silent rule that governs our understanding of thermal interactions. In this lecture, we will systematically unpack the zeroth law and its implications. We will cover three key areas. First, we will precisely define the zeroth law of thermodynamics, carefully explaining its wording and the concept it introduces. We will explore its logic and uncover why it's necessary for the consistent definition of temperature. Second, we will go deep into the concept of thermal equilibrium, understanding how the zeroth law guarantees the equality of temperature when systems are in thermal contact. This equality of temperature is at the heart of many thermodynamic processes and calculation. Third, we will briefly touch upon the concept of energy and its various forms, while at least acknowledging the central role of energy in all thermodynamic processes. By the end of this lecture, you will have a clear and comprehensive understanding of how temperature is defined and measured. That is because of the zeroth law of thermodynamics. You will appreciate why energy is a crucial player in thermodynamic systems. And you will see how these concepts work together to lay the groundwork for more advanced topics in thermodynamics. So let's dive and begin our exploration of the zeroth law, unlocking its significance and revealing its essential role in the world of thermodynamics. To truly understand the zeroth law of thermodynamics, let's start with a relatable common scenario. Imagine you have three distinct objects. Let's call them object A, object B, and object C. Suppose we observe that object A is in thermal equilibrium with object B. What does this mean? It means that if we brought object A and B in thermal contact, means allowing them to exchange the energy, no net heat will flow between them. They are already at the same temperature. And next, let's say we also observe that object A is in thermal equilibrium with object C. Means object A and object C both are also not interchanging their heat. Means they are at same temperature. Similarly, if we brought this A and C in thermal contact, no heat will flow. They too are at the same temperature. Here's where the zeroth law comes into picture and plays a crucial role. What the zeroth law states is, if A is in thermal equilibrium with both B and C independently, then B and C must also be in thermal equilibrium with each other. In simpler terms, if two systems B and C are each separately in thermal equilibrium with a third system A, then they must be at the same temperature and they will be in thermal equilibrium with each other. This might seem obvious, but its implications are profound. Essentially, it tells us that thermal equilibrium is a transitive property. It allows us to establish a common reference point for temperature. This law forms the basis of temperature measurement. As we know, it allows us to define and compare temperature consistently across different systems and locations. We can use thermometer, that is our object A, to determine the temperature of different objects, object B and C, and know that if the thermometer reads the same for both, then those objects are also at the same temperature. Without zeroth law, we could lack this fundamental basis. Sorry, without zeroth law, we will lack this fundamental basis for comparing temperatures. We won't be able to establish a universal temperature scale, making the analysis of thermodynamic systems incredibly complex and frankly unreliable. It provides the justification to use a thermometer as a reliable measurement instrument. Now that we have laid this fundamental principle, let's explore some alternative ways of stating the zeroth law and further solidify our understanding. The zeroth law of thermodynamics will elegantly stated in terms of equilibrium between multiple systems can also be expressed in a simpler, more direct manner. If two systems are in thermal equilibrium, they must be at the same temperature. This statement encapsulates the essence of zeroth law. It highlights that temperature is a fundamental property that directly dictates whether heat will flow between two objects or systems. If they are at the same temperature, they are in thermal equilibrium and no heat transfer will occur. Temperature is the deciding factor. From this core concept, we can draw a few key takeaways. First is no temperature difference, no heat transfer. If two objects or system possess the same temperature, there will be no net heat transfer between them. They are already in equilibrium. Temperature difference drives heat transfer. This is a second takeaway. On the other hand, if two objects have different temperatures, heat will flow from the hotter objects to the cooler objects. This heat transfer will continue until thermal equilibrium is achieved, meaning until both objects reach the same temperature. It's important to emphasize that this principle holds regardless of whether the objects are in direct physical contact, while conduction heat transfer through direct contact and convection heat transfer through movement of fluids are common modes of heat transfer. Then the zeroth law also applies for the radiative heat transfer. For example, think about placing your hand near a fire without actually touching it. You can still feel the warmth even at the distance. This is due to thermal radiation, where the fire emits electromagnetic waves that carry energy to your hand. The principles of the zeroth law still apply. Your hand is cooler than the fire, so it absorbs radiative heat until or eventually thermal equilibrium is reached. Though that would require a significant amount of time and you would likely move your hand before then. Therefore, understanding the zeroth law helps us to explain a wide range of phenomena from cooling of a hot cup of a coffee to the warming of the earth by the sun. It's a fundamental principle that governs thermal interactions in all their forms. Now we have established the foundation with the zeroth law. Now we will go deep into concept of thermal equilibrium itself. In essence, thermal equilibrium is the state where there is no net heat transfer between the object or surrounding or the system that are in thermal contact, even though they are capable of exchanging heat energy. It's not the heat transfer can't occur. It's that the rate of heat transfer in both directions is equal, resulting in no overall change in temperature. This is a dynamic equilibrium. A classic example is what happens when you bring two or more bodies at different initial temperatures into contact. Heat will flow from the hotter object to the cooler object until they eventually reach a common intermediate temperature. At this point, they are said to be in thermal equilibrium. The rate of energy transfer from the hotter object equals the rate of energy transfer to the cooler object. Consider this in everyday's example. First, take an example of hot tea cooling. When you place a hot cup of tea in a room, the tea is initially much hotter than the surrounding air. Heat will transfer from the tea to the air, gradually cooling the tea down. Sorry. This process continues until the tea reaches the same temperature as the room. Once this happens, the tea and the room are in thermal equilibrium. Now take another example of cold drink. This cold drink which we keep in the room, what is going to happen? If you place a cold drink in a warm room, the drink will be colder than the surrounding air. Heat will transfer from the air to the drink, gradually warming the drink up. This process continues until the drink reaches the same temperature as the room, at which point they are in thermal equilibrium. To bring this concept, let's consider a real-life example that most of us encounter regularly. That is a refrigerator. When we put food in a refrigerator overnight, the food is usually warmer than the air inside the fridge. The refrigerator's cooling system removes heat from the air and this cool air then absorbs heat from the food. Eventually, the food and the surrounding air inside the fridge reach the same temperature. At this point, they are in thermal equilibrium. The refrigerator continues to run, removing any heat that leaks in from the outside to maintain this low temperature equilibrium. This concept of thermal equilibrium is crucial for understanding how temperature regulations work in a wide range of engineering applications, from the design of refrigerator and air conditioners to the development of industrial cooling systems and power plants. By understanding how systems reach thermal equilibrium, engineers can design more efficient and more effective thermal management solutions. Okay. One of the common direct and common applications of the zeroth law of thermodynamics lies in the everyday act of temperature measurement using a thermometer. In fact, it's impossible to build a reliable and accurate thermometer without relying on the principles enshrined in the zeroth law. So, how does a thermometer actually work? Let's break down. The first is the thermal contact. When you place a thermometer in contact with a substance whose temperature you wish to measure, whether it's water, air, or anything else, heat transfer begins to occur between the thermometer and the substance. Next is the reaching of equilibrium. This heat transfer continues until the thermometer and the substance reach thermal equilibrium. As we have discussed, thermal equilibrium means that there is no longer any heat transfer or heat flow between the two, and crucially, they now share the same temperature. Third is the temperature indication. The thermometer is designed to exploit a temperature-dependent property of a specific material. In a traditional mercury or alcohol thermometer, this property is the thermal expansion of the liquid. As the temperature increases, the mercury or alcohol expands, rising in the calibrated tube. As the temperature decreases, it contracts, falling in the tube. The height of the liquid column is then read against a scale to determine the temperature. The zeroth law is that which makes this process happen. Because the thermometer and the substance reach thermal equilibrium, the thermometer accurately reflects the temperature of the substance. Thus, the zeroth law makes accurate temperature measurement possible. It forms the very basis for all temperature scales that we use, including Celsius, Fahrenheit, and Kelvin. Without the zeroth law, we would have no guarantee that the thermometer was actually reading the temperature of the object, and we won't be able to establish a reliable and consistent temperature scales. It gives us confidence in the reading we take, allowing us to perform accurate calculations and make sound judgments about the system's behavior. A profound consequence of the zeroth law of thermodynamics is that it follows us to rigorously define the concept of the equality of temperature. It provides the logical justification for saying that two different objects have the same temperature. What exactly does the equality of temperature mean in context of the zeroth law? It means this, that let's call a system A and system B are each separately in thermal equilibrium with a third system, that is our reference system C. Then system A, system B must have equal temperature. This principle, seemingly simple, is the cornerstone that allows us to develop standardized temperature scales and compare temperatures accurately across diverse systems and environment. It gives us a reliable way to say this is hotter or this is colder, regardless of the specific circumstances. Let's consider some practical examples. Defining the boiling point of water. If we place a thermometer in thermal equilibrium with the boiling water under standard atmospheric pressure, we can reliably define the temperature as 100 degrees centigrade or 212 degree Fahrenheit or 373.15 Kelvin. This definition is consistent because the zeroth law tells us that the temperature or the thermometer and the boiling point are at the same temperature when they are in thermal equilibrium. Any other system in thermal equilibrium with that same boiling water will be also at 100 degrees centigrade. Coming on for definition of the melting point of ice, if we place a thermometer in thermal equilibrium with the melting ice, again it should be at standard atmospheric pressure. We can reliably define that the temperature as 0 degrees Celsius or 32 degree Fahrenheit or 273.15 Kelvin. These fixed points defining or which are defined using the zeroth law allow us to calibrate thermometers and establish consistent temperature scales. Without the zeroth law, we could have no consistent objective way to measure and compare temperature across different environments or with different instruments. Temperature would be a relative, ill-defined concept, making meaningful thermodynamic analysis impossible. By providing the basis for equality of temperature, the zeroth law provides the foundation upon which all other temperature measurements and thermodynamic calculations are built. Now, we have built a solid foundation in temperature and thermal equilibrium thanks to the zeroth law. Let's shift our focus to another cornerstone of thermodynamics, that is energy. Understanding energy, its forms, and how it interacts with the system is crucial for comprehending nearly every thermodynamic process. In the simplest terms, energy is the capacity to do work or to produce heat. It's the fundamental driving force behind all physical process. Without energy, nothing would happen. Energy exists in variety of forms, each representing a different way that this capacity to do work or produce heat can be manifested. Let's briefly outline some of the key forms of energy that are relevant to thermodynamics. First is the kinetic energy. This is the energy of motion. Any object that is moving possesses kinetic energy. The faster it moves, the more kinetic energy it has. Examples include a spinning turbine, a flowing fluid, or even the movement of molecules within a gas. Next is the potential energy. This energy is stored energy due to an object's position or configuration. Examples include water held behind a dam due to gravitational potential energy, or a compressed spring which consists of elastic potential energy. The third important form of energy is the internal energy. This is the sum of all the microscopic, kinetic, and potential energies of all the particles, atoms, and molecules within a system. It includes the energy of their random motion, their vibrations, and the forces between them. Internal energy is a state function, meaning it only depends on the current state of the system, not on how it reached that state. And the important energy which is we are going to discuss is the thermal energy. This is the portion of the internal energy that is specifically associated with the temperature of the system. It's the energy associated with the random motion of the molecules. Higher the temperature, the greater the thermal energy. Thermodynamic systems exchange energy with their surrounding through two primary mechanisms. First is the heat and other is work. Heat is the transfer of energy due to temperature difference, while work is the transfer of energy due to a force acting over a distance. These energy exchanges are rigorously governed by the laws of thermodynamics, which we will explore in future lectures. Understanding energy role is essential for analyzing and designing efficient and effective thermodynamic systems. Now let's look closely to particularly important form of energy in thermodynamics that are thermal energy and internal energy. While they are closely related, understanding the deeper concept of these energies is essential for accurately analyzing thermodynamic systems. Coming on to the thermal energy, as we briefly touched upon in the previous slide, thermal energy is the energy specifically associated with the temperature of a system. More precisely, it represents the total kinetic energy of the particles, including atoms and molecules that make up the substance. The higher the temperature of a system, the more vigorously its particles are moving and the greater its thermal energy. Thermal energy is the energy responsible for the phenomena like heat transfer. Coming on to the internal energy on the other hand is a broader concept. It encompasses all the energy contained within a system at the microscopic level. This includes not only the kinetic energy of the particles, which is what thermal energy means, but also the potential energy arising from the forces and interaction between these particles. This potential energy can be due to the chemical bonds, intermolecular forces, or even the nuclear forces. It is the sum of all forms of energy that is stored within a system. Understanding these two forms of energy is absolutely essential for analyzing thermal processes. These processes include heat transfer. As we know, heat transfer is the exchange of thermal energy between systems or between a system and its surrounding, which is driven by a temperature difference. Next is the work done process. Work is the transfer of energy that occurs when a force acts over a distance. This can be work done by the system, For example, like a gas expanding and pushing a piston, or a work done on the system like compressing a gas. And the final important process is the energy conservation. The principle of energy conservation, a cornerstone of thermodynamics, states that energy cannot be created nor destroyed, only transformed from one form to another. Understanding the various forms of energy, particularly internal and thermal energy, is crucial for applying this principle correctly. Finally, it is worth to know that the zeroth law of thermodynamics plays a crucial role in establishing the relationship between temperature and energy. By defining thermal equilibrium and the equality of temperature, the zeroth law provides the foundation upon which we can build our understanding of energy transfer and transformation in thermodynamic systems. It is the basis for connecting temperature to energy at a microscopic level. Now it's time to summarize the key concept we have explored in today's discussion. We have covered a lot of ground from the seemingly simple but profoundly important zeroth law to the fundamental concept of energy. First, we have defined what is the zeroth law. It states that if two systems each independently in thermal equilibrium with a third system, then those two systems must also be in thermal equilibrium with each other. This establishes thermal equilibrium as a transitive property and allows for a consistent definition of temperature. Next important concept was understanding of thermal equilibrium. Thermal equilibrium occurs when there is no net heat transfer between objects or systems, even if they are in thermal contact and capable of exchanging heat. This is the state of balance where the rate of energy transfer in both directions is equal. The third is the zeroth law and temperature measurement. Zeroth law provides the foundation for accurate temperature measurement using thermometers. By allowing the thermometer to reach thermal equilibrium with the objects being measured, we can reliably determine the object temperature. This also forms the basis for all standardized temperature scales, that is Celsius, Fahrenheit, and Kelvin. And finally, we have discussed the energy and its forms. Energy is capacity to do work or transfer heat. It exists in various forms, including kinetic energy, that is energy in motion, potential energy, that is stored energy, internal energy, that is the total microscopic energy of a system, or the energy which is possessed by the molecules of a system. And finally, the thermal energy. It is the portion of the internal energy which is associated with temperatures. These concepts, the zeroth law, thermal equilibrium, and energy, are absolutely fundamental for understanding how heat and energy interact in real-world systems. They provide the language and the framework for analyzing everything from the operation of a refrigerator to the efficiency of a power plant. By grasping these core principles, you are well prepared to go deep into the fascinating world of thermodynamics and to apply this knowledge to solve practical engineering problems. That concludes our lecture for today. Thank you very much for your attention and your active engagement. I hope this has been a clear and informative exploration of the zeroth law and its implication. Now, I will also be happy to address any questions that you may have.